Hey y'all, this is Dallas here with a lecture about fission and the chain of nuclear reactions that occurs in power plants and atomic bombs. You should have completed 4.4a, the fission FET, either doing the actual simulation or watching me do a walkthrough of it. If you haven't done that, go back, take a look at it at least before watching this lecture. It'll help to have that context. All right, so quick, what is nuclear fission? It's the splitting of the nucleus of a radioactive atom into two smaller nuclei. Nuclei is the plural of nucleus. So we're taking a bigger atom and breaking it apart into two chunks. Sometimes there are other small pieces that fly off too, but these are going to be radioactive things. So they're not stable right in the middle of the band of stability. They are radioactive. And as it turns out, most of them are radioactive because they're so heavy, like uranium and plutonium. There actually aren't any stable forms. Now, why do we care about nuclear fission? The type of reaction releases a great deal of energy. A crazy small amount of material releases a ridiculous amount of energy. So if you look here, the picture is a little pellet of uranium-235, about the size of a pencil eraser, and it releases as much energy as 1,000 kilograms of coal. So there's a huge advantage there in terms of just the size of the power plant you need, and obviously if you're not burning coal, you don't have any of the emissions problems that we have with coal-generated power, such as carbon dioxide, soot, heavy metals. So a quick schematic. In the beginning we have uranium-235, and it says stable, but that means relatively stable. It is radioactive on its own, but it takes a long time for it to break down. So it's relatively stable. Uranium-235 is hit with a neutron. So this neutron goes flying in there, and you can see that the mass number in the middle is increased to 236 because it has that extra neutron, but it's still uranium because the number of protons didn't change. Now this guy is really unstable, and so it's going to fall apart almost immediately. And as it does that, you can see it's kind of here splitting down the middle, breaking up into two different chunks. Very often this is krypton and barium, and we can see there are 1, 2, 3 neutrons at the end here that are also released. So most of the material is in these two elements, which are a lot more stable, and then there's also some neutrons involved. Okay, so to kind of walk you through step by step, number one, a uranium-235 nucleus gains a neutron. So at the start of the chain reaction, we have to shoot in a neutron, and you saw that in the 4.4a FET simulation. There was a gun that shot in the neutron. But once the reaction has happened and we make those 3 neutrons at the end, those neutrons can go off and start the process over. So the neutrons released previously as products can start new reactions during a chain. The uranium-236 nucleus becomes extremely unstable with that extra neutron. It's messing up the ratio of neutrons to protons, which makes elements stable. And then it splits into 2 small nuclei and releases multiple neutrons. So, example, krypton-92, barium-141 are common products, but they're not the only ones. I don't want you to think that's the case, but we just talked about them a lot. And multiple neutrons that get made can strike the new uranium-235 atoms. So we go from here back up to here. All right, now we use nuclear equations to show what's happening in the reaction. And here I have a summary, kind of just all the stuff at the beginning and all the stuff at the end, kind of skipping over that middle step. So on the left-hand side, these are the isotopes and elements before the reaction. You'll notice I'm including both the mass number and the atomic number and the symbol. There's a plus sign indicating that it's this one and that one. N is for neutron, symbol for neutron. Neutrons have a mass of 1, but they don't have an atomic number because there's no protons there. The arrow is indicating that there's a nuclear reaction happening. So we're going from the stuff on the left to the stuff on the right. So I've got the krypton, the barium, and if I want to show 3 neutrons, I could do this 1 over n symbol plus the 1 over n symbol plus the 1 over 0 n symbol 3 times. But like in math class, I could combine like terms. X plus x plus x is 3x. So 3 neutrons, put a big 3 out front, and then a little superscript, small number in the upper left, subscript, small number in the lower left, and then the n. Okay, so we're going to start to talk about some of the reasons why we show the mass number and the atomic numbers here. But take a look here, 92 plus 0 on that side, 36 plus 56. Maybe you're not great at mental math, but take a guess. What do you think that adds up to? All right, now, spoiler alert. The mass numbers of the reactants add to be the same as the mass numbers of the products, and the atomic numbers of the reactants add up to the atomic numbers of the products. So to show you that, 235 plus 1, 236. We first make uranium-236, right? The numbers in red add up to each other. And even easier to see, the atomic numbers 92 plus 0 add up to 92. Now, that should always be the case when we're doing nuclear equations. The numbers on the bottom should equal each other on the left and right of the arrow. Same thing with the numbers on the top. And to show you that second step again, everything in blue should equal each other. So 92 plus 0 is 92. And 36 plus 56 is 92 plus 0 plus 0 plus 0. So 92 on the left, 92 on the right. In red here we have all of the mass numbers, and they add up to 236 on this side. 92 plus 141 plus 1 plus 1 plus 1 adds up to 236. And you can see here I've shown that the neutrons are separate from each other just to make the math a little bit easier to see. Okay, so our next question is, how does fission result in so much energy? And simply, it's not because it happens one time, although one fission reaction does produce relatively a lot of energy, but because it happens again and again and again and again, then we really get so much energy. So we'll see if this guy is going to work here. So we can see the one neutron strikes the uranium atom, which strikes more uranium atoms, which strike more uranium atoms. And we have the products shown as purple and green elements. And all of these little guys here, the small dots, are more neutrons. As the reaction goes, it makes more and more and more and more and more of the fission reactions. And eventually, if we have enough of the element called the critical mass, it's a self-sustaining, that there are enough uranium atoms around that the neutrons that are produced can make more and more and more. For uranium-235, it's the size of a cantaloupe. And so, interestingly, when you're trying to build an atomic bomb, but you don't want it to go off, you have to make sure that you have enough uranium there, but you don't want it all together in one place. And so commonly they'll have 2 halves of the cantaloupe separated from each other inside the bomb. And then when you want it to go off, you kind of combine the 2 halves back together. So it's reached this critical mass. All right. And so if you'd like, this is a pretty cool video sponsored by Pepsi Max. It's the ultimate chain reaction created by 2014 mousetraps and 2015 ping pong balls. How many atoms must undergo fission to start a chain reaction? Well, the answer is 1. Okay. Notice here that just have 1 extra ping pong ball representing the 1 neutron you have to add at the start of the reaction. And then, as you can kind of see in the image, we can get the mousetraps to go off. It's a pretty good video. if you're looking for something to do after listening to me, check it out. Make sure you fill out the guided note sheet if you haven't done that already. And if you have any questions about Fission, please let me know.